Kind of take a moment and look at an approach that the IB takes for energy cycles. Right? And these are using general energy cycles. And the first one we're going to look at actually incorporates the enthalpy of formation. Right? In our energy cycle here, we've got reactants and products, and then we have the elements. The reactants go to the products, you will get the enthalpy of the reaction. From elements to the reactants, you'll get the delta H of formation of the reactants, and the sum of those, all of the elements that would go to make up the reactants. And from the elements to the products, we would have the sum of the enthalpy of formation for the products. So how I tend to look at these is I say, okay, if I take this path, so my red path, okay, that's the delta H of the reaction. Okay. I can get from reactants to products by also going this way. Now the arrow represents I guess just the direction. So when I go from reactants to elements, the delta H actually becomes negative. So it's negative the sum of the heats of formation for the reactants. And then I'm going in the direction for the sum of the delta H heats of formation for the products. That's how you kind of look at an energy cycle. So it's kind of, the direction you're going is going to be, if the arrow is going the other way, it would be a negative. Okay, but it still works kind of the same as we looked at those energy diagrams. I find the energy diagrams easier to follow, probably just because I'm used to it. So we'll take another look at this when we're done talking about standard enthalpies of combustion. What we're going to try to do now is define and apply the term standard enthalpy change of combustion, and then to determine the enthalpy change of a reaction using these standard enthalpies of combustion. These are again tabulated in your book, your reference book for IB. I will make a table available. Eventually you'll get the whole data book to use in class and for tests and for the IB test. All right, but that's what they look like. Delta HC, standard heats of combustion for different compounds. Okay. All right, so how do we use these? That's the same definition. Again, standard conditions, 25 degrees Celsius, 1 atmosphere, which is the same as 101 kilopascals, same as 1.00 times 10 to the 5th pascals. Okay, we have this other diagram, and you notice it looks a little different than it looked in the previous slide. Okay, if we go back there just real quick. So the heats of formation are from the elements going to the compounds, and then elements going to the compounds, which is the reason for the direction of those arrows. If we look at the heats of combustion, it is the reactants being combusted or the products being combusted. So that's why the arrows go this way. Okay, we can still calculate the overall enthalpy of the reaction. Okay, going from reactants to products going in this way, I would get the change, the enthalpy of the reaction is going to be equal to the sum of the delta heats of combustion of the reactants, and then minus the sum of the heats of combustion for the products at standard state. So this is different than the heats of formation. For the heats of formation, it's going to be products minus reactants. When we use heats of combustion, it's going to be reactants minus products. And it's really how those values are defined. maybe we can go through a Hess's law kind of problem to look at it again. All right, so what we want to do now is write the thermochemical equation which represents the standard enthalpy of combustion of hexane. Hexane, you may be thinking to yourself, we haven't learned organic compounds. How am I going to know what hexane is? Here, enthalpies of combustion, also useful to identify the formulas for organic compounds. Hexane is C6H14. So, we can use that. So I have C6H14. Did you happen to see what the state of matter was? Well, let's go back real quick. Hexane is a liquid. Oops, I didn't need to do that. Hexane is a liquid. When you combust something, it has to react with oxygen. What is it going to form? CO2 gas and H2O liquid, because we're at 25 degrees Celsius and 1 atmosphere. So now we're going to balance it. 6 carbons gives me a 6 there, gives me a 7 there. 6 times 2 is 12, plus those 7 is 19. So I have 19 halves of oxygen. Now it asks for a thermochemical equation, so you know I have to somewhere find the delta H of the reaction. Well, where do I find that? Hey, it's right here. Try to move it a little bit so we can read it. So hexane, the combustion, is negative 4163 kilojoules per mole. Okay. So, whoa. What was it? Negative 4163 kilojoules per mole. Okay? Alrighty. Oops. So let's calculate the enthalpy of formation for glucose using the enthalpies of combustion values from table 12. Well, the first thing I want to do is write the equation for the formation of glucose. I'm going to get a full empty screen here to work with. All right, so I want to form C6H12O6, which is a solid. I'm going to form that from its elements. Well, from carbon, hydrogen, and oxygen. Those are the elements that makes it up. So carbon, in its elemental form, we learned before, is graphite. Plus H2 as a gas, plus O2 as a gas. I have 6 carbons in the formula, so I need 6 over here. This becomes a 6. This becomes a 3. Now the question also asked me to calculate the enthalpy of formation using the enthalpy of combustion values. Well, from what we just looked at, the enthalpy of reaction using combustion values is going to be the sum of the HC for reactants minus the sum of the heats of combustion for the products. Okay, so I want to pull this table in. And I will get 6 times the graphite. Graphite is negative 394 kilojoules per mole, plus 6 times hydrogen. Hydrogen is negative 286 kilojoules per mole, plus 3 times oxygen. Oxygen's nowhere on this table. It is actually 0. That's the reference point. Minus the combustion of glucose, which is negative 2803. It's down here. Okay. So minus the negative 2803 kilojoules per mole. If I do all that math, I should come up with a value of negative 1277 kilojoules. So that's using heat of combustion to calculate enthalpy of reaction. And remember, the difference between using the heats of formation